We'll move on to our last talk in this section on quantum communication in cryptography. It will round off this section by addressing on a more broad term, or more broadly, the full range of threats coming from quantum computers to cybersecurity. Our speaker is Duncan Jones. He's the head of quantum cybersecurity at Cambridge Quantum Computing. He holds a degree in computer science from the University of Cambridge, and he has over 13 years of experience developing security solutions for global companies before his current role already. So, hello Duncan, welcome to the Quantum Summit. On stage, Bob. It's great to have you with us, and I'm very excited to see and hear your talk now. The stage is yours, Duncan.
Thank you very much. Good morning, everyone. My name is Duncan Jones, as we've heard, head of quantum cybersecurity at Cambridge Quantum Computing. If you're not familiar with Cambridge Quantum Computing, or CQC as we're known, we're a quantum software company. We're 7 years old now, so we were started back when quantum computers really weren't so popular as they are today. And we have teams looking at basically every area where quantum computing is thought to bring some advantage, whether that's quantum chemistry, quantum machine learning, or natural language processing, and cybersecurity, which is the team that I lead. I fundamentally believe, as I'm sure this audience does, that quantum computing is going to change the world. And so a few, let's say maybe a year ago now, I began looking for somewhere that I could combine my interest in quantum with my long background in cybersecurity. And that led me to CQC. And we spend our time looking at how quantum technology can enhance cybersecurity. And it truly allows us to do some things that have never been possible before. But this talk is going to be, I would say, quite a high-level, accessible walk through what are the actual challenges that quantum computers pose to cybersecurity, and then ultimately what we can do to address those concerns. Now, we'll start, as all fun presentations do, with a small maths test, so brace yourselves. Now, if I asked you to solve this equation on the screen, so we need to find two numbers, and they're prime numbers, that multiply together to equal 15, I don't think you will find this very difficult. The answer is, of course, 3 times 5. Now, notice even at this very simplistic stage that it's slightly easier to go in one direction here than the other. If I give you 3 times 5, you'll instantly give me 15. We've been practicing that since we've been children. But if I give you 15 and ask you to break it down, it's just slightly harder. And it gets harder still when the numbers get larger. So if I ask you now to break 187 down into the 2 prime factors that make it, this is a lot harder because you're probably trying to remember what prime numbers are. You're trying to figure out what are the prime numbers, the first few of them, and doing lots of division and things in your head. And some of you may get to the answer, which is 11 times 17. Now here it's even more obvious that going in one direction is easier than the other. If I give you 11 times 17, hopefully you can get to 187 in your head. I like to do 10 times 17 and then add one more 17. It's quite doable, but the reverse is difficult. And as we get to larger and larger numbers, this becomes no longer possible to do in our heads. 1,517 is more than large enough that I can't do that in my head. And no matter how many times I present this particular slide, I keep forgetting that the answer is 37 times 41. So why am I giving you a math test? Why am I talking about this? Well, this kind of asymmetrical operation where it's hard to go in one direction, but easier to go in the other direction is actually what we use today to build some of our most important encryption systems. Of course, we don't use numbers like 1,517. We use numbers like this one, which is large enough that I have no idea how to actually pronounce it. But computers today are very comfortable at taking two very large prime numbers and multiplying them together and achieving this answer on the left-hand side. But actually, no classical computer could ever do the reverse operation. So if we give a classical computer this large number and ask it to break it down into the two prime factors that compose it, it cannot be done. And this is what underpins algorithms like RSA and keeps our information secure today. Now, the reason I'm talking about all this is because, unfortunately, quantum computers can actually solve this type of problem very effectively. As I'm sure you all know, quantum computers don't magically solve every problem, but certain types of problems they can solve surprisingly effectively. And unfortunately, this prime factorization problem is one of those things that quantum computers can really accelerate. And this is the person that we can blame for this. This is Peter Shor, who is a mathematician. He's done a lot of work in quantum computation. And back in the 90s, I think 1994, he derived an algorithm, which we now call Shor's algorithm, which shows us how a sufficiently powerful quantum computer can do this factorization. And that's quite a problem because that then breaks a lot of the cybersecurity solutions that we rely upon today. Now, notice I said sufficiently powerful. So it requires us to have enough functioning qubits in order to execute his algorithm, in order to break sufficiently large cryptographic keys. So then the question you may naturally ask is, okay, when will quantum computers actually do this? When will they be powerful enough to crack encryption? And I would encourage you, and I guess my sort of primary message today for you is to wonder whether that might be the wrong question to ask. We will come back to this, but I think it's the wrong question to focus on, because what companies need to be thinking about is, when do we need to act? When should we actually do something about this? And to answer that, I'm going to give us talk through a small example. So imagine your company is sending some encrypted data somewhere else. It doesn't really matter where, to a third party, maybe to another part of your organization if you're large enough. But imagine this is, the most sensitive data that your company processes. Maybe it's customer data, healthcare data, personal data, financial predictions. Every company has got something highly sensitive that it's sharing today. Then imagine that you have an attacker listening into that communication today. Now, fortunately, that attacker can't read your information today. And by the way, when I say attacker, don't just think, some kids wearing hoodies on their laptops. We're talking about sophisticated attackers that use nation-state funding to achieve what they want to achieve. Those attackers are quietly listening in and recording the information. They know they can't attack it today. RSA has not been broken. So these communications are absolutely safe today. But these attackers are thinking ahead to the somewhat near future, where quantum computers will break encryption. And that means they can retrospectively crack into the information that has been shared. And that's the horrible part of it. It's retrospective. So you have to think to yourself, well, what information am I sharing today that would have some value to an attacker or to a nation state in 5, 10, 15 years' time? Which then brings us back to the question of, well, when is this going to happen? So nobody knows for sure. The CEO of Google last year gave quite an aggressive prediction, suggesting that in as little as 5 to 10 years, we'll be in a position where quantum computers will crack encryption as we know it today. And that was last year, so you could maybe argue it's 4 to 9 years away. But whenever it is, it's not too far away. And the question is, are you sharing information today that would be sensitive in that time frame? And I think most of us are. But it gets worse than this. This is where most people's discussion of the threats may come to an end. But we need to go deeper. We need to actually think about keys themselves. So cryptographic keys, if you're not really that comfortable with them as a concept, it's quite helpful just to think about physical keys. If you have a physical key and you lock a box, and then you send that box to somebody, well, they can open that box as long as they've got the same key. Obviously, in a digital world, keys are not physical objects. They're streams of zeros and ones. And the security of these keys is basically down to how unpredictable are those zeros and ones. To have a completely secure key, those zeros and ones need to be completely random. If an attacker can guess even 1 or 2 bits of that key, they can actually break into the messages that we're sending to people. So it's critical these things are highly random. The question then comes, well, what happens if we have quantum computers examining not just the keys that we generate, but the methods that we use to generate keys? Because the other thing quantum computers are very good at is finding patterns in data and simulating very complex systems, exactly the type of systems that we use today to generate our keys. And in that future, I believe quantum computers are going to start to find patterns in our keys that we didn't even realize were there. And this is just another way that quantum computers are going to make cybersecurity particularly challenged. I mean, they're going to be able to find patterns and simulate the complex systems we use to generate these keys. And that's going to give attackers another edge in the near future. So enough doom and gloom. What are we actually going to do about these challenges? So let's paint a little path ahead to a safer future. So we had 2 problems. So let's talk about 2 solutions. So the first problem was the fact that the algorithms themselves are not going to be robust in the face of quantum computers. And simply, we're going to have to switch to new algorithms, ones that rely on different mathematical problems. There are plenty of mathematical problems out there that quantum computers can't solve any better than classical computers. The second problem was around keys and their predictability, and how do we keep them from being predicted by quantum computers? And the answer is we move towards different methods of key generation that produce perfectly unpredictable keys, so that quantum computers have no advantage against them. On the first solution, we are largely relying upon NIST in the US, who have launched a competition back in 2016 to find these new algorithms. And slowly over the last few years, we've been whittling down the candidates. We started with 69, we're down to 7 finalists now. And in the next year or 2, we're going to settle on some winners. Probably more than 1 winner, in fact. Now, this is great. It means everything's in hand, but I would encourage you not to relax. I think, in fact, everybody needs to start working on proof of concepts today. And this is because these algorithms are not trivial swap-in replacements for the algorithms that we use today. In fact, they all have different behaviors and characteristics. And so the sooner people experiment with this stuff, the better. So you can experiment with any of those candidate algorithms today, and you'll be in a better place when we start to move towards them. And also, moving early protects you against that threat we discussed about having your data recorded and decrypted at a later date. On the key generation side, which was solution 2, how do we defend against quantum computers predicting our keys, we actually turned back towards quantum computers to give us the answer. So as I'm sure this audience will be very aware, that quantum computers allow us to create states that are combinations of, let's say, a 0 and a 1. So if you create a qubit that is in a state that is 50% 0 and 50% 1, you can measure it, and perhaps you'll get a 0 on the first occasion, and then you'll get a 1. And if you keep repeating this process, you get very unpredictable outputs. And that's exactly what we're looking for to solve this problem. And in fact, that's what we've been working on at CQC for the last few years. We use this output from this is a simplified example, but we use outputs from quantum computers to generate perfect randomness that we can prove it's perfect. And then that allows us to generate keys that are unpredictable. And they are unpredictable against today's attacks, and they're also unpredictable against any attack in the future that could be accomplished by a quantum adversary. So that was a fairly quick tour through the challenges facing cybersecurity and some of the solutions and what they might look like. And what I want to close with, or make sure everyone is focusing on, is that question I raised a few slides ago now about what the right thing we should be thinking about is. And it's not to focus entirely on when quantum computers will crack encryption. It's to focus on when do we need to do something about it. We have these two very clear problems. Algorithms will be broken and keys will be predicted. When do we need to act on them? I hope it's clear that the answer is now. We have algorithms that we can experiment with today, and we have solutions like the one from CQC, which is ready today. It only requires 3 qubits to execute, so it's something that we already offer as a commercial service today. The answer's out there, and I hope you guys start to explore it today. Thank you.
Thank you, Duncan. Thank you for this very interesting and nice talk and lining out to us the threads. And what I particularly liked, I have to say, is this very easily understandable explanation in the beginning of how prime factorization works. I think everyone can relate with the, okay, this is easy, and hey, this is not so easy, and this is really difficult. And understanding this first, and then seeing, okay, so quantum computers can this is where they this is their attack vector, so to say. This is where they have the advantage. I think this is a very, very nice approach here. Thank you so much for being with us. I don't see questions right now from the audience, but that doesn't mean there are none. And you will be available for another... Oh wait, there is one coming. I was just about to send you off already to the speaker's corner, but there's one coming in now. It's can you comment a bit more on how a quantum computer can identify the encoding scheme?
I guess this probably refers to my... I'm assuming this refers to the key generation piece. So I'll answer it as though that is the case. But if that's not right, please join the speaker chat afterwards and we can dive deeper. I mean, the short answer is we don't know exactly what adversaries are going to do when they have access to quantum computers. But we can assume that they will use those machines to help model the systems that we rely upon today to generate keys. So there are a variety of different techniques that are used today to generate keys, and they produce output that looks random to us because it's based on chaotic physical systems that, as humans, we struggle to understand. But quantum computers in the future will be able to model those, I think, and see them as deterministic systems that just progress from state to state to state. And that's what we need to move away from. We need to move to non-deterministic methods of key generation.
Okay, thank you. There's one more question referring to the last statement of the presentation. It was what was the 3-qubit approach?
Oh yes, so this is our protocol that we use on quantum computers to generate provable randomness is a 3-qubit protocol. In fact, we have a paper that describes this, and I'll find some way to make that available to people. It's on our website otherwise. But that's what I'm referring to. This is the protocol that we run on a quantum computer to generate these perfect keys.
Okay, thank you for that too.